All right, we'll get started. Hopefully we can get through today without serious interruptions like last time. Um, so for those of you that were here last time or heard otherwise, we did have a fire alarm that cut us off about 20 minutes early. So that recording is now up. So I updated the recording to include all of that and the notes as well. Maybe I forgot to post the notes. So I'll have to check on that. I got busy last Tuesday. But anyway, once the notes are posted, they'll be complete and the videos up there as well, on YouTube. So we're not going to go back and cover that today. But the good thing is the stuff that we missed at the end last time is going to kind of be superseded by what we cover at the beginning of today anyway. So what we're going to cover today is sort of a more complete version of all of that. That's really the best way to approach that material in most cases. So you won't be missing too much, but you should still take a look at it on your own nonetheless. All right, so we're continuing on with our discussion of ideal gases, which is the major topic of this chapter. So what we ended with last time was, well, we would have ended with last time if the fire alarm didn't cut us off. But anyway, we had three different gas laws that were all determined by relationships between the volume of a gas and some other parameter. So the one that we had just started covering when the fire alarm went off was Boyle's law. And this one says that the volume and pressure are inversely proportional. So when the volume increases, pressure decreases and vice versa. So we write it mathematically as volume is proportional to 1 divided by the pressure. And then you can sort of come up with an equation for that is sometimes useful, where P1V1 equals P2V2, meaning if the pressure and volume are changing, the product of the two at the initial and final states has to remain equal. Sometimes that's a useful equation, but as we're going to talk about today, we're going to come up with a combined equation that's always the best to use as our starting point. For Charles's law, which is the second one that we would have covered, we spell it right. That one says that volume and temperature are directly proportional. So if you increase the temperature of a gas, all else being constant, you're going to increase the volume and vice versa, which can be written as V1 over T1 equals V2 over T2. Now, just as a warning that I gave in the end of the lecture, that's now just going to be a recording. Whenever you see equations involving gases that have temperature in them, in this case, it has to be in Kelvin. So if it's absolute temperature, no delta in front of it, just the temperature by itself, these units have to be Kelvin for the temperature. And then the last one is Avogadro's law, which is what Avogadro was actually known for more than the number. The number was kind of just an homage to him. This one says that volume and number of moles are directly proportional. So in this chapter, we're going to use N as the abbreviation for number of moles, and those two for a gas are directly related, which you can then write as V1 over N1 equals V2 over N2. So we have these three equations, and sometimes it's hard to know which one to use, or sometimes we might be relating two things that don't fall under these two gas laws. So what we're going to do is we're going to take these three things here. We'll take these three things here, and we're going to combine them by taking the product. So something we talked about a little bit in chapter 7 when we were introducing the equation for heat, which was Q equals MC delta T. If you have a variable, a parameter that's proportional to two or more different things, it will also be proportional to the product of those things. So what we can say in this case, volume is proportional to 1 over pressure, to the temperature, and to the number of moles. So volume would also be proportional to the product of those two things, or those three things, sorry, 1 over P times T times N. So then if we want to avoid having things in the denominator, we can just multiply both sides by P to get P over on the left side. So we can write that pressure times volume is proportional to the number of moles times the temperature. So that's just a rearrangement of that by multiplying both sides by pressure. So now what we have is a proportionality. As we talked about last time, if you want to take a proportionality and turn it into an equation, you just need a constant on one side of that. And so what we can do is we can put the constant on the right side and call it R, and that gives us the equation PV equals nRT. Now, this is a very useful equation because pressure, volume, number of moles, and temperature are the only four things you need to know about a gas. Those are the only four properties that are related to each other in this way. So that means this R here is a universal constant. It's a set value. It's on your periodic table. And the one that's going to be most commonly used is the one that has units of liters and atmospheres. So 0.0821 liter atmospheres for the volume and pressure units divided by Kelvin has to be temperature always, and then moles in the denominator as well. So those are the units for that, but that's the value. And again, for any sample of gas, it doesn't matter what the identity of the ideal gas is, whether it's hydrogen, oxygen, nitrogen, pick your favorite ideal gas, it's going to follow this equation and use that same universal gas constant R. So R is called the universal gas constant because it applies to all gases, and when you're using this equation, it will never change. And we call this PV equals nRT an equation of state because it describes everything we'd ever want to know about a gas. The pressure, volume, number of moles, and temperature describe all the key properties of a sample of gas, and they're all related in this way with that single constant on the one side. So this form of the equation here, going forward, I think whenever we have problems that involve gases changing their condition, so some combination of changing one or more of these variables here in a sample of gas and figuring out what happens to the other one, this is going to be our starting point. We don't necessarily have to remember all three of these individual equations up here. They're still useful, they're still valid, but if we always start with PV equals nRT, as I'll show you today, that can always be the place that we derive whatever relationship we need between the two or more properties that we're considering in that specific problem. Okay, so let's do some examples of this just to see all the different ways we can use this. All right, so we have 0.1 mole sample of neon gas occupies a volume of 2,503 milliliters and exerts a pressure of 551 torr. What is the temperature of the gas? So in this problem here, this is one where we're not changing anything. We're just giving you an amount of the gas, a volume, and the pressure, and we're asking you to solve for the fourth thing, the temperature here. So that's one sort of type of problem we could do. It's the simplest of them, I suppose, because you're just using this one equation here, PV equals nRT, and solving for whatever your unknown is. So again, in this problem, we know the number of moles, we know N, we know the volume, which is that number there, we know the pressure. So all we're going to do is use this equation to solve for temperature. So we can just rearrange and say that temperature is equal to pressure times volume divided by the number of moles times R. And we just start plugging numbers in. Now, the thing we have to be careful, though, is if we are using R as part of our calculation, there will be problems where that R kind of drops out. But in this case, we have the value of R in there in the denominator, and we have to, again, pay close attention to the units. So I've been harping on you all semester to write out your units. Some of you do that, some of you don't. You can choose whether or not to listen to me. That's your free will. But I always suggest writing out the units. And what we'll see here is that if we have the units for R, it's liter atmospheres K mole. Temperature has to be in Kelvin. That's non-negotiable, and that's what we're solving for here. So that number will be in Kelvin. But we can have different values of pressure and volume especially. But if we're going to use this value of R, we have to report those in liters for the volume, atmospheres for the pressure. So in this problem here, we have to do some conversions because the pressure, which is the first thing going in here, is in torr. We need to convert that into atmospheres if we're going to have standard value of R in this equation. So we have 551 torr, and one of the only unit conversions you'll have to worry about in this chapter besides temperature is just 1 atmosphere is 760 torr. So you have to get familiar with that. So that's going to be 0.725 atmospheres. So that would be the value we want to use for pressure in this equation in the units that we need it to be. Volume, as we said, has to be in liters because of the value of R. So we have to do that conversion as well. Milliliters to liters is one we've done a lot already in the previous chapter, so should be familiar with just 1 liter is 1,000 milliliters. So we divide by 1,000 to go from milliliters to liters, and I get 2.503. So that one we probably could have done in our head. So that's the value for the volume in the correct units. And then in the denominator, we have number of moles. There's only one unit for moles, which is moles, so you don't have to convert anything there. 0.100, it's already in moles. And then R, as we said, has to be, if we're using this standard value, the one that's found on your periodic table, we go there, and then we just work it out, and we get 221 Kelvin. We did not specify a unit, but if you wanted to convert this to Celsius, you would subtract 273 and get minus 52. All right. Now, hopefully this helps us understand why temperature has to be in Kelvin. Here, we're solving for temperature, as I said, but you can't use Celsius temperatures because it is possible they'll be negative or zero, and you can't put a negative or a zero into this equation and have it work. You're never going to have a negative pressure or negative volume, so you can't have a negative temperature either. And so your temperature has to be in Kelvin because that one goes, as always, a positive number. It starts at zero and goes up from there. So we get 221 Kelvin or minus 52 Celsius for this one if we subtract 273 from that. All right, any questions on that? All right, so that's one variation of the type of problem you could do with PV equals nRT. The much more common ones are going to be ones like this, where we have the properties of a gas changing, and we're trying to figure out then what happens to one of the other parameters. So let's say we have a balloon that has a volume of 255 milliliters, 912 torr, and 25 Celsius, and then we let it float up into the atmosphere where to a point where the temperature and pressure are minus 23 Celsius and 2.28 torr. What is the volume of the balloon under these conditions? So in a problem like this where conditions are changing, sometimes one of the simpler equations that we introduce for Boyle's law, Charles' law, Avogadro's law will work, but it's not going to be the case here because here we see that we're trying to figure out how the volume changes. That's what we're looking for here. But we see that both the pressure and the temperature are also changing. So there's not one of those simple equations that relates all three of those things. So whenever we need a relationship, we can always derive it from PV equals nRT. So if we use this as our starting point, the first thing we want to do at the beginning of the problem is figure out which of these four parameters, PV, N, and T, are going to be constant, if any of them. So if you're looking for the one that's constant, it'll either be, sometimes it'll be given to you numerically and it'll show that it's not changing, or sometimes you have to infer it from the problem. So if you have a problem that involves a balloon or any sort of closed container, you would assume that the number of moles of gas is constant. We're not having gas leaking in or out of this. It's just a closed container of gas, so N will stay constant the whole time. So in this problem, the number of moles is constant because we're dealing with a closed container. Anytime your container is closed, we're not adding or losing gas from that, then your number of moles is constant. And generally speaking, in a problem like this, if we don't tell you anything about one of these values, we didn't tell you how many moles there were, we didn't tell you that it was changing at all, you would just assume that it has to be constant. You don't know anything about it, so nothing you can really do with that anyway. So we'll assume the number of moles is constant because we don't say anything about it, and in this case, it is a closed container as long as you don't have a leak. So then what you do is you take PV equals nRT, and everything that's constant, you move over to one side of the equation and rearrange it. So here, number of moles is constant. R is always a constant. It's just a single number. So we're going to move those things to one side and move everything that's changing over to the other side. And we're going to get this PV over T equals NR as a rearranged form. And remember, this product here is a constant. So because pressure times volume divided by temperature is constant, that means in the initial state and the final state, this fraction here, PV over T, is going to have to be the same before and after whatever changes occur. So we can rewrite it then as P1 V1 over T1 equals P2 V2 over T2. So basically, those are the three things that are changing, and we can get this relationship between them because that has to be constants. That means the product and the ratio before and after have to stay the same. So we rewrite it this way where whatever variables are changing, we set up like this, and then we solve for what we're looking for. So we're looking for the final volume V2. So you can either put numbers in first or do your algebra first, whatever you prefer. I usually do the algebra first. So solving for V2 by just cross multiplying and dividing, we get P1 V1 times T2 divided by T2 T1. I usually write it like this, where the two things that are the same are kind of on top of each other, but whatever order you put them in will be fine. So that's how we're going to solve for V2. We just need to put everything in here. Now, once we do this type of approach where we've rearranged the equation and solved for whatever things are changing and sort of working it out like this, we don't have the value of R in here anymore. So we don't necessarily have to use the standard units of liters and atmospheres. Temperature has to be in Kelvin, so don't ever screw with that. But when you're talking about, in this case, pressure and volume, they can be whatever units you want them to be as long as R has dropped out of the equation like it has here. So what that means then is, well, we don't have to change anything except for the units of temperature. So when we put everything in, the pressures are both in torr, but we can keep them that way because the two are going to divide by each other and the units will cancel out anyway. So we can put P1 in as the initial pressure of 912 torr. We can put the initial volume in as 255 milliliters. And then in the bottom here, we're going to have P2, which is 2.28 torr. And then we have T2 over T1. So we have to put the temperatures in Kelvin, though. That's the only thing we have to change here. That has to be the case. So T2, which is the final temperature, is minus 23 degrees Celsius. We add 273 to get it into Kelvin, so it's going to be 250 Kelvin. So that's T2. We have to make sure we put everything in the right order. That's one of the only things you have to be careful about in these types of problems. Make sure your T2, T1, all those are straight. 250K for T2, T1, 25 degrees Celsius plus 273 is 298 Kelvin. So I put that here in the bottom for T1. So when we do this, the pressure units divide out. We kept them as torr. We don't have to change them. It wouldn't be wrong to change them. You get the same value, but it's just less steps to do it this way. Units of temperature cancel out. They have to be in Kelvin. And then we're left with a volume in milliliters would be our final answer. So again, writing out units for this is going to be very helpful. So this comes out to 85,570 milliliters, which is 85.6 liters. Now, this is kind of an physically unrealistic problem because we're taking a balloon that's about the size of a can of pop and we're blowing it up to the size of a 20-gallon fish tank. Probably not going to survive that change in volume unless it's the world's strongest balloon, but that's the numbers that we get out of this, okay? I think I just said pop. What do you guys call it here? Soda? Okay, sorry. Now you know where I'm from. All right, so we have 85.6 liters is the value that we get there, or 85,570 milliliters, but the answers that they want are all in liters, so we'll choose that one. All right, so when we're doing problems like this where conditions are changing, we just have to isolate the units that are changing, the parameters that are changing, and kind of set an equality like this to solve for what we're looking for. So any questions on that? All right, so this one here is just another example. So we have a gas cylinder with fixed volume. Yes, so we have fixed volume, which means volume is constant. And so again, in problems like this, if we have something that's constant, it'll typically drop out for us. So we have a fixed volume. It has 239 moles of hydrogen and a pressure of 136 atmospheres. 176 moles of hydrogen are removed from the cylinder. What is the new pressure reading? So this would be a relationship between pressure and number of moles, which is not one of the standard gas laws. So again, starting with PV equals nRT is going to be the way to go here for any of these types. So we have PV equals nRT. Fixed volume tells us that the volume is constant. And then the other one, which doesn't say anything about, is temperature. So we didn't say anything about temperature, so we can't put in a value for it. So again, we have no choice but to assume that it's constant. We're not told about it. And then this universal gas constant R is always a constant. So those are the three things that are constant. It would be pressure and number of moles that are changing. So we isolate all those to one side. So the two things that are changing are pressure and number of moles. So we put them on one side, and then on the other side, we have RT over V. And you could write it either way. We have over here P over N equals RT over V. We could write it as N over P equals V over RT. As long as you're properly doing algebra to rearrange this equation, however you do it will be fine. And that equals a constant, okay? Which then tells us that this ratio here, P1 over N1, which are the two things that are changing, equals P2 over N2. So it's a way of saying that pressure and number of moles are directly proportional to each other. So we just solve, we're looking for the new pressure, P2. And so we just solve for P2, which is going to be P1 times N2 over N1. So mathematically, this isn't too bad, but one of the reasons that I wanted to give you this problem is to make sure we understand what exactly we mean by number of moles here. So in this problem, we have the initial pressure is 136 atmospheres. So we're going to put that in directly. But then we need the two values for the number of moles. All right, so N1, which is the initial number of moles, is given to us directly, 239. So that's going to go down here. We don't have to change anything there. But we have to be careful with what we put in for N2, because here we're telling you that 176 moles of hydrogen are removed from the container, but that's not going to be the value that we want to use for N2, because this equation here reports for how many moles of gas are actually present, not how many we took away. So this final number of moles here is going to be the initial number that we started with minus the amount that we removed. This equation will always report how much gas is actually present, not how much we took away. So we're starting with 239 moles. We're subtracting 176. So what's left in the container after this is 63 moles. So that's the value that we want to use for N2, the number of moles that are present after this change occurs, after we've let some out. So 63 moles is the number that goes in here, not the 176, which is how much we took away. And so then once we do that, the math is easy and it comes out to 36 atmospheres. All right, so we've removed about 3/4 of the gas and we lost about 3/4 of the pressure as a result. All right, any questions on that? So again, any relationship between 2 or 3 of these values here can come about from just starting with PV equals nRT. So you'll see a lot more problems like this on the homework. I just gave you a couple here to give you a flavor, but again, follow this same approach. Figure out what's constant, move it all over to one side, and then set up a relationship that relates whatever is changing and go from there. So you have to be a little bit careful with units, especially for temperature, but in most cases, if R drops out, you can choose whatever unit you want or just use what's given to you as long as they're consistent with each other in the numerator and denominator. Okay? So the next thing we're going to cover, which is very much related to, oh, sorry. I guess because when we subtracted these two numbers here, if we're following the rules for sig figs, you get a number that only has two. So that's why I did it that way, which would be correct. Again, we're not that picky about sig figs in this course. If you had reported your number to 3 sig figs, it would not have been caught kind of wrong. Just that little bit of rounding, but technically it should be 2 because when you subtract these two, you get a value here that's 2 sig figs. All right, anything else? Okay, so then what we're going to cover next is an equation and relationship that involves the density of a gas. So we haven't really talked about density much at all in this course. We introduced it in the review chapter. It's the ratio of mass over volume for any substance, but it is something that's going to come up now in these last two chapters, first in the context of gases and then a little bit in for liquids and solids as well. Now, gases are the least dense of the 3 states of matter. But sometimes talking about the density of a gas is still relevant and still useful. And we can calculate the density of a gas using PV equals nRT as our starting point. So again, this is an equation of state for a gas. So it's really the one unifying equation that we need to describe just about everything. But if we want to have density involved with this, remember that density here is mass over volume. This equation here has the volume in it, but doesn't have anything about mass. But if you recall stuff that we learned back in chapter 5, the number of moles here can be rewritten as the mass divided by the molecular weight or the molar mass. So that's the relationship we use all the time in chapter 5, relating mass and moles. So we can then, where here M is the mass in grams, and then molecular weight is the molar mass in grams per mole. All right, so that's a relationship that came up a lot in the previous couple chapters. So we can rewrite PV equals nRT by substituting N with mass divided by molar mass. So it comes out to PV equals mass over molar mass times RT. And then we want to solve for density, which is mass over volume. So we just have to do a little bit of algebra. mass over volume, we just move volume over, we move molecular weight over to the other side as well, and we get pressure times molar mass divided by RT. All right, so this equation here can be used to calculate the density of a gas. I don't know if we have a problem exactly like this in today's lecture. We don't, but another useful application of this equation is that because it includes molecular weight, as we talked about a little bit in chapter 6 with some of the titration problems, if you're trying to identify an unknown substance, one of the pieces of that puzzle often is going to be what's the molecular weight of this substance. That can give you a clue to what the formula might be. So if we know the density of a gas and we know its pressure and its temperature, we can actually solve for what the molecular weight is as a way of identifying unknown gases. This is part of that process. So that's going to be some things you might see in the homework. It's the same exact equation, just in some cases you'll actually want to solve for the molecular weight as a way of identifying something that's unknown. But this problem here that I have is just kind of a simpler one. So we're just looking here for the density of ammonia if the pressure is 500 torr and the temperature is 37 degrees Celsius. So we're going to use that exact equation that I just gave you, rearranging PV equals nRT. You don't necessarily have to memorize this equation separately because it comes straight from PV equals nRT if you remember a little bit about how I derived it. But that's all we need is those three things: pressure, molar mass, and temperature. And so we just start plugging things in. Now, in this equation here, as we're using it, it does include the universal gas constant R. So once again, we have to be mindful of the units that we're using. So we need a pressure here, which is going to have to be in atmospheres for this to work if we're using the standard value of R. So we'll have to convert that pressure value into atmospheres first. Assume that this has 3 sig figs. It has a little, I forgot to put the little period there, but 500 torr, and then 1 atmosphere is 760. So we'll get 0.658 atmospheres for the pressure in the correct units. Just a conversion. And then we have to calculate the molar mass of ammonia, something that should be commonplace for us now, calculating molecular weights or molar masses. NH3, I'll save the time of not going back and forth to the periodic table, but here we have a nitrogen and 3 hydrogens. Nitrogen has an atomic mass of 14.01. Hydrogen has an atomic mass of 1.01, so we just add 1 nitrogen plus 3 hydrogens together, we get 17.03 grams per mole as the molar mass for ammonia. And then here in the bottom, we have R, the universal gas constant. You could always have different values of this if you change the units, but we'll just keep it in the standard form, which is given to us in the periodic table. And then the temperature has to be in Kelvin for any of these types of problems. So don't forget that. Temperature in Kelvin is 37 degrees Celsius plus 273, which is 310 Kelvin. All right, so those are the numbers that we put in. The only one where we had to change the units were we had to change the units of both pressure and temperature in this case for this to work, but we just plug in and we get 0.440. Now, when you first look at that number, you might think like, well, I thought you told us that gases were a lot less dense than liquids. Well, the density of water is 1. This one's like 0.44, and the pressure's not even very high. So, is that really true? But pay close attention to the units. This is grams per liter. The density of water is grams per milliliter. So this is over 1,000 times less dense than water because it's a per liter. So gases are at typical conditions, with regular sort of near atmospheric pressures and temperatures that are commonly found, you would get densities that are on the order of about 1,000 times smaller than typical liquids like we have here. Okay. And as I said, this equation here will sometimes be useful in other ways, especially for solving for molar mass. So you'll see some of that as well. One other thing that I should probably point out, because I don't know if I have it later on in the notes, and so before I forget, I'll just tell you. What you might also see sometimes in gas law problems like this, any of the ones that we've done today, is this abbreviation here, STP, which stands for standard temperature and pressure. And so that tells you that the pressure is exactly 1 atmosphere and the temperature is exactly 0 degrees Celsius or 273 K. So if you see STP in any of these problems, those would be the pressure and temperatures you would use, because we might sometimes ask you, what is the density of this gas at STP? So in that case, we won't explicitly give you the pressure and the temperature, but you would know from the abbreviation STP, that means 1 atmosphere and 273 Kelvin. So sometimes I forget to point that out until the exam review, so I want to make sure you get it earlier than that. So there it is. I don't think I have any problems in the notes like that, but okay. So any questions on that stuff? Now, the other thing that the ideal gas equation is going to allow us to do is return to our favorite longtime friend in this course, stoichiometry, and using PV equals nRT as part of a way of calculating the number of moles of gas in the context of a stoichiometry calculation. So let's review then all the different ways now we have to determine the number of moles. And we're going to use the abbreviation N now that we've been using in this chapter. So we started with early on in chapter 5, the definition of a mole, which is that it's the number of entities, particles, atoms, molecules, whatever it's made up of, divided by Avogadro's number. We talked about a little bit today and a lot in chapter 5, this relationship here, where the number of moles is the mass in grams divided by the molar mass in grams per mole. In chapter 6, we talked a lot about this relationship involving aqueous solutions or other types of solutions where the number of moles is equal to the molarity, capital M, times the volume V. So that was used a lot in solution stoichiometry or titration problems. And then what we now have introduced in this chapter, which is the last relationship involving moles that we're going to use. So this is going to be it. PV equals nRT, which means that we can solve for the number of moles if we know the pressure, the volume, and RT. And then, so that allows us then, if we have samples of gases, if gases are involved as reactions or products, if we know their pressure, volume, and temperature, we can also then determine the number of moles and then use that as part of a stoichiometry calculation. Since, as we've already talked about a lot, any stoichiometry calculation typically would start with finding the moles of the substances involved. So for gases, this is one way to do it. Now, another thing that I want to point out, because again, I don't think I have any example problems like this, but you might see them, and it can make things a lot easier for you than the way I have to do it today. You'll see from this equation that number of moles is proportional to the pressure and the volume. And so what that tells us is that, let's say we have a gas phase equation, combustion of hydrogen, simple one here. All of them gases. So if we know the pressure, volume, and temperature of all 3 gases involved, we can do calculations involving moles like we normally would. But also, because the number of moles is proportional to the pressure and proportional to the volume, these coefficients that we have in the chemical equation can be interpreted as number of moles like they typically are, or in terms of pressures and volumes of gases for anything that's a gas in these. So again, these are all 3 gases. And so if we have these coefficients here, 2H2 plus O2 goes to 2H2O. The standard way of reading that would be 2 moles of hydrogen reacts with 1 mole of oxygen to make 2 moles of H2O. But because number of moles is proportional to volume, if all the gases are at the same temperature and pressure, we could also say that 2 liters of hydrogen reacts with 1 liter of oxygen to make 2 liters of water. So for gas phase stoichiometry, when somewhere all the reactants or products are gases, the mole ratios are also equal to the volume ratios at which they react. That was kind of another statement of Avogadro's law that we covered earlier. So you can also, sometimes you can simplify the problem because you can do things directly in volume units without having to necessarily convert to moles all the time. Or as we'll learn a little bit later today, you can also define what are called partial pressures, which are the individual pressures of gases in a mixture. And so if we know those, we could say that 2 atmospheres of hydrogen and 1 atmosphere of oxygen react to make 2 atmospheres of water. And again, it's because this relationship that states that number of moles is proportional to pressure and to volume. And so that means mole ratios in a chemical equation can also be interpreted as either volume or pressure ratios for things that are gases. So that's going to help us out in some of the homework questions that you'll see. The problems we're going to do in today's assignment that may or may not be useful. But anyway, let's go through some. So here we have one where nitrogen and fluorine are combined in a 1 to 3 mole ratio at a total pressure of 1.25 atmosphere, which forms NF3 quantitatively. If the reaction is carried out at constant temperature and volume, what is the final pressure at the end of the reaction? So this is kind of a strange problem, I would say. Maybe not the best one to start with, but we'll go ahead and do it. So we have a balanced equation here, which is given N2 plus 3F2 goes to 2NF3. So in this problem here, there's a few different ways of approaching this. But we are telling you here just the ratio that these things are combined at, a 1 to 3 mole ratio. We're not telling you the exact amount. But it turns out, because of the way the ideal gas equation works, where what we're looking for here is final pressure, and that's proportional number of moles, it doesn't really matter what number we choose for the individual moles. If we want to do real numbers for this, we can just assume that we just have 1 mole of N2 and 3 moles of F2. And then we're going to form 2 moles of NF3. Okay, so simple stoichiometry. We told that they're combined in 1 to 3 ratio. We gave you the total pressure initially as 1.25 atmospheres. And we just want to figure out what is the pressure at the end of the reaction. So we can just assume whatever numbers we want, as long as the ratio is 1 to 3, we'll get the same answer. So the way that we can approach this is that at the start of the reaction, the total number of moles of gas that we have is 4, because we have 1 mole of nitrogen, 3 moles of fluorine. Something we'll formalize a little bit more detail in just a few slides from now is that if we have a mixture of gases, all that really matters is the total number of moles, and we're determining the pressure. So they can be multiple gases mixed together. If we know the total moles, that's going to relate directly to the pressure. So we have 4 moles initially of reactants. Our final state, we're forming 2 moles of our product here. So at the end, we only have 2 moles of gas as products because of the coefficients in the chemical equation being what they are. So we can kind of then set this up as an ideal gas problem where we know that the temperature and the volume are constant. The only thing that's going to be changing is pressure and number of moles. And so we can set up the same relationship we did earlier, where we isolate pressure and number of moles because those are changing. RT over V is a constant in this problem, constant temperature, constant volume. And so then we can write it as P1 over N1 equals P2 over N2. Where in this case, we're not just physically changing the number of moles of gas, but we're doing a chemical reaction, which then changes the number of moles of gas. So initially, we're at 4 moles of gas. At the end, we're at 2 moles of gas, and we can just set it out this way. So the final pressure then would be the initial pressure times the ratio N2 over N1, just rearranging this relationship here. The initial pressure was 1.25 atmospheres at the start, and then the number of moles that we just figured out. So at the end of the reaction, we had 2 moles of gas. At the start of the reaction, we had 4 moles of gas. So when we calculate that out, the final pressure then would be 0.625 atmospheres. So we have half as much gas at the end of the reaction as we started with, which means the pressure would also be cut in half. So that was kind of a strange one. It wasn't really a gas stoichiometry problem, although it did help us. It did involve a little bit of stoichiometry insight to get this final number here. But really, it was just an ideal gas problem. So maybe not the best one to start with, but anyway, any questions on that? All right, this one here is going to be a little bit more involved, but I think it's a good one because it sort of combines a lot of different ideas that we've had both in today's class and some things we covered in the past. So we have this reaction here where we take phosphine gas pH3, react it with oxygen, and make P2O5, which is a solid under these conditions, and then gas phase water. So there's a lot of questions we're going to ask about this, but let's just set up the problem first. So the way that we can often do gas phase reactions is we have two separate bulbs, two separate containers of gas that are separated. So initially, pH 3 is in flask A, O2 is in flask B, and we're giving you information about each of those. So the temperature is 400 Kelvin for the whole thing, but we have this is 12.5 liters, and it's 2 atmospheres. This bulb B over here is 10.0 liters with a pressure of 3 atmospheres of gas inside. So initially, we just have the two gases separate like that. And then they're joined together by this valve here, C, which is just a little glass valve that you can turn, and you open up that valve and allow the two gases to mix together and react. Okay? So the first question here, we're going to take this in parts, is how many moles of gas are present at the start of the reaction? So this is one, as we talked about, where if we're doing a gas phase reaction, we can use PV equals nRT. And if we know the pressure, volume, and temperature of the gases, we can solve for the number of moles just by rearranging that equation. So if we want to find the moles of each gas, we just need to know the pressure, volume, and temperature, which we have for both of them. So for the first gas, pH 3, the number of moles is going to be, its pressure is 2 atmospheres. That's stated directly in the problem. 2 atmospheres of pH 3. It's in a volume, a bulb that has a volume of 12.5 liters. Universal gas constant R here in the bottom. And then the temperature is 400 Kelvin, already in the right units. Temperature of the whole thing is 400 Kelvin. So what we get for this is 0.761 moles of pH 3. And then the moles of oxygen. The pressure for oxygen was 3 atmospheres. So the pressure in the two containers are initially different from each other because they are completely separated. So that is possible. The volume of that container was 10.0 liters. Same gas constant for all gases. So that number never changes. And then the temperature, we said, for the whole thing was 400 Kelvin. So that comes out to 0.914 moles of oxygen. So we used PV equals nRT to calculate the moles of each gas. And now that we have them, we can go forward and treat this like a regular stoichiometry problem. In any stoichiometry problem, we typically start by finding moles of reactants and then calculating something that we're asked to do. And now we have moles of both reactants this way, just using the ideal gas equation to get those instead of the other relationships that we covered earlier. So the second part of this then asks if the valve C is opened and the gases mix and are allowed to react, which of those is the limiting reactant? So once the reaction starts, we have to figure out what the limiting reactant is because we have moles of both reactants. That's what this is asking us about. So this is just a review of chapter 5 stuff. We just figured out that the moles for pH 3 was 0.761. The moles for O2 was 0.914. That was a calculation we did in the previous slide. So if we want to find the limiting reactant, there's different ways of doing that, but my preferred approach is just to find the stoichiometric ratio R, where we take the number of moles and we divide it by the coefficient. So the coefficient for pH 3 is 2. So its stoichiometric ratio is 0.38. 2 digits should be enough to compare. The stoichiometric ratio for O2, we would take its number of moles, which is 0.914, and dividing it by 4, which is the coefficient for oxygen, and we get 0.23 for that. So this is our smaller stoichiometric ratio, which tells us that O2 is the limiting reactant. Now, if I was, this is an aside, this is not important, I suppose, but if I was the professor and a student was setting up this reaction, I would scold them for the way they chose to do this because they're taking something that's horribly toxic, pH 3, and using it as the excess reactant, which means that that horribly toxic gas is still going to be present at the end, as opposed to O2, which is pretty benign. So I would not do the reaction this way, but again, we follow the numbers that are given to us, and we find that O2 is the limiting reactant. And then once we know that, there are many other stoichiometry things we can do. So part C is how many grams of this product here are formed. So we know that O2 is the limiting reactant, so we're going to start with that to find the mass of the product that forms. We have 0.914 moles of O2, which is our limiting reactant, and we just use coefficients in the balanced equation to find the moles of product that would form from that. 1 mole of P2O5 has a coefficient of 1 in front of it, an implied coefficient of 1, over 4 moles of O2. And then we want to convert to grams of P2O5, so we use the given molar mass of 141.94. So now it's just a stoichiometry problem, so we should be off to the races. So moles of P2O5 cancels, moles of O2 cancel. That gets us grams of P2O5, which is 32.4. And we can go on from there, but there are things that we could calculate, but we're going to stop there in the interest of time. So some other things that you could think about possibly being able to calculate then would be, and this was just the standard stoichiometry part, but we could also calculate how many moles of gas are left at the end of the reaction. So that would involve how much excess pH3 is there, plus how much O2 H2O gas forms. That would give us the number of moles of gas at the end. And then from that, we could calculate the pressure at the end of the reaction, where the combined volume was the sum of the two. So there's other things that we could do with this, but we're going to stop there in the interest of time. But with gas stoichiometry, as we showed here, sometimes PV equals nRT is useful to allow us to get the number of moles of each substance, especially if we know the pressure, volume, and temperature. You can always approach it that way. In other cases, like I said earlier, for gas stoichiometry, you would just use the volume ratios of the gases. We couldn't do that here because the two gases are at different pressures. But if the two gases are at the same pressure, just the volume ratio is all you would need to start doing a stoichiometry problem. So you'll see some of that and variations of that on the homework. So that'll be a good learning tool for you. But the next major topic we have to cover, which is all still related to the ideal gas equation, it's not anything totally different. It's called Dalton's law of partial pressures. So this is going to deal with situations where we have a mixture of two or more gases, kind of like the air that we breathe, for example. Anytime we have two or more gases mixed together, how do we talk about the pressures of those gases and some relationships involving that? So we're going to start with a little bit of a thought experiment here. Okay, so imagine you have a flask that's filled with 1 atmosphere of nitrogen, so a balloon or a flask, some container, closed container. And then you pump an additional 1 atmosphere of nitrogen into there. What is the total pressure? Does anybody think it's A, B, C, or D? Do you have any votes for A? 1 vote for A. What about B? Solid number of votes for B. C? And then I would assume the rest of you are going to choose choice D because most of you didn't raise your hand. All right. Now the correct answer for this is B. So that tells us that pressures are additive. So if we know the individual pressure of a gas and we add a certain amount of additional pressure to that, we just add the two pressures together. They are completely additive as long as the volume is fixed. Okay, so in this case, it has to be a fixed volume closed container. So that was the same. Now in this one here, we were using the same gas, 1 atmosphere of nitrogen, 1 atmosphere of nitrogen. Now let's do a slightly different one where we have 2 different gases. If you have a flask with 1 atmosphere of nitrogen and you add in 2 atmospheres of O2, so different gas this time. They're both gases, but there's 2 different ones now. What would the total pressure be? Is it, anybody think A? We have a B, C. All right, most of you got it, and then D. All right, so that's correct. So the gas pressures are going to be additive regardless of whether it's the same gas being combined with more of that same gas or 2, 3, 4, however many different gases being combined together. If you know the individual pressures of each gas that you're mixing together, the total pressure of the mixture is just the sum of all of those. And that's because all gases will follow that same ideal gas equation, PV equals nRT, which is not determined by what gas you have or anything about the identity of it. All right, so the key points from all of this is that the pressures are additive whenever we have a mixture of gases. It's also important to note that gases mix homogeneously, particularly if they're ideal gases. We'll talk a little bit at the end of this chapter about what happens when gases are non-ideal, we're assuming everything's ideal for now, and they follow the PV equals nRT equation, so they would mix homogeneously. They're going to be completely interdispersed with each other. And what that kind of means then is that each gas in a mixture behaves as if it were the only gas present, which allows us, as we said, to sort of treat the individual pressures of those components separately from each other, and the two or more things that are mixed together don't really exert any sort of influence on each other. They still follow the ideal gas equation, and they don't really even care or realize that there's another gas around them. They just still behave ideally with the same sort of relationships involved. So that's kind of the starting point for when we're talking about mixtures of gases. So this then led to a more sort of detailed and mathematical formulation called Dalton's law. So Dalton was one of the earlier chemists that sort of formulated a lot of these things. And this is, again, is an equation and a principle that applies to mixtures of two or more gases. All right, so if you have a mixture of two or more gases, this is when Dalton's law would apply. All right, so there's different ways of sort of stating this. What we gave you just a little bit ago was that the total pressure is additive when you have a mixture of gases. So if you know the individual pressures of the two or more gases that are mixed together, you can just add them together to get the total pressure. So that's one formulation of Dalton's law, very simple one, where again, these PA, PB, PC are going to be what are called partial pressures. Where that's going to be the pressure of one of the individual components that's in the mixture. And if you know those individual pressures, those partial pressures as they're called, you can just add them together to get the total pressure of the mixture. Now, in terms of number of moles here, we can, again, use PV equals nRT and note that the pressure of any gas is equal to nRT over V. So if we have a mixture of gases, they're going to be at the same temperature and the same volume. They're all interdispersed together. And then that means the total pressure would be the number of moles of gas A times RT over V. We're just rearranging this equation here in terms of nRT over V, plus the number of moles of B times RT over V, plus the number of moles of gas C times RT over V, and however many you have, which we can sort of factor out RT over V, Na plus Nb plus Nc is just the total number of moles of gas. So that kind of gets at what came up in one of the earlier example problems I did, which is if you have a mixture of gas and you want to know the pressure of that gas, you just need to know the total number of moles of gas. It doesn't matter how many of each gas you have. It doesn't matter what the ratio of them is. If you know the total number of moles of gas, you can calculate the pressure regardless of how many gases are mixed together. But then probably the most commonly used form of Dalton's law is in terms of what's called mole fraction, which states that if we want to calculate the partial pressure of a gas, a lot of times we don't know what the individual partial pressures are, but we do know the total pressure. We know how much gas we mix together. If we want to calculate what the partial pressure is, it's going to be given in this way: chi times the total pressure. So this is Greek letter chi, which is called the mole fraction, and is defined as the number of moles of that gas divided by the total number of moles of gas in the mixture. So on some level, pi here is just another concentration unit. It's telling you what the ratio of one gas is in a mixture as a function of the number of moles of gas for that one over the number of moles that are total. So what that allows us to do then is take this additive formalism that we started with, actually, I don't need to do this. I'll just stop there. This always confuses people when I do it that way. This is going to be the form of Dalton's law that you're going to most commonly use, so make sure you're familiar with it, which is that the partial pressure of a gas in a mixture is the mole fraction of that gas multiplied by the total pressure. And then if you were to add up all of the partial pressures, that would give you this number here, the total pressure. Okay. All right. So any questions on that? Just sort of the sort of theoretical framework of it. All right. So then we're going to do a couple example problems. So let's say we have a mixture of two gases that has 40 grams of oxygen and 40 grams of helium with a total pressure of 0.900 atmospheres. What is the partial pressure of O2? So this is the more typical way that you'll see Dalton's law problems set up, where we're actually trying to calculate the partial pressure of a gas in a mixture. So we just use that equation I gave you. We're looking for the partial pressure of O2. So we need the mole fraction and the total pressure. The total pressure is given to us in the problem, but we have to find the mole fraction of oxygen to be able to get this. So the mole fraction of O2 is going to be the number of moles of O2 that we have divided by the total number of moles of gas, which is going to be also stated as the moles of oxygen divided by moles of oxygen plus helium. There's only two gases in the mixture, so that's how we would do it. So we have to do some math to get the moles because we're given the masses of each gas. And none of these ideal gas equations, except for the density one, really involve mass at all. So we need to find number of moles typically for any of these types of problems. So we're going to find the moles of O2 just by using its molar mass. So we have 1.25 moles of oxygen. Then I have to do the same thing for the other gas, helium. Even though we're not solving for the partial pressure of helium, we do need that here to figure out what the total number of moles that we have are. So the moles for helium is going to be, we also have 40 grams of that, but its atomic mass, its molar mass is much smaller. It's only 4. So that would come from the periodic table, 4 grams per mole for helium. And so we have 10 moles in this mixture. So to get the mole fraction, we take the number of moles of oxygen, which is 1.25, and we divide it by the sum of the two, 1.25 moles for oxygen, 10.0 moles for helium, and that ratio comes out to 0.111. All right, so that's the mole fraction of oxygen, and so then what we end up with is 0.111 multiplied by the total pressure, which is 0.9, comes out to 0.0999 atmospheres. So it's kind of an interesting look at this because even though we have equal masses of the two gases, 40 grams of each, it turns out that the partial pressure exerted by oxygen is much smaller than that exerted by helium because its mole fraction is so small. Only 11% of the mixture in terms of moles is going to be oxygen, even though they're 50-50 by mass. All right, so any questions on that? So pretty simple equation. There's some different ways of using it, but mostly it'll be like this. But then the other application of Dalton's law that we could have is in gas stoichiometry. So this is kind of a convoluted setup, but this is one that you might see, so I want to make sure we understand it. So what you can do is one way to measure gases that are involved in a chemical reaction. So let's say you're doing a chemical reaction that produces a gas as a product, and you want to do an experiment in the lab that measures how much of that gas is formed. I don't know if you guys actually do this in your chem lab or not, but the way it would work is you would have your reaction is taking place in some sort of a vessel like a test tube. So you have a reaction going on there that produces gas. So here it's KClO3 and MnO3. I think it produces oxygen. I'm not sure what the product that would be, but this is just a demonstration. So the gas that's produced is going to travel through this apparatus. Gases always expand to fill their available volume. So this gas is going to travel through and be transported to the collector. And then what ends up happening is the way we collect it is it's through a tube of gas that is inverted into a container of water where we can measure the volume. So the gas bubbles basically float to the top of the surface and they push the surface of the liquid down. So basically the surface of the liquid is going to drop as more gas is collected up here above it. So that basically the amount of volume change that you have in that liquid is going to correspond to how much volume of gas you produce in the reaction. A lot of times you'll do this with a graduated cylinder. We have an upside down graduated cylinder. completely filled with water initially, and then the amount that that level drops by tells you the volume of gas that's collected above that water. All right, so the gas displaces the water in the collector, and that's how we measure its volume. So one thing that we have to recognize to be able to do this, though, is that in these experiments, we're going to know what the total pressure of the gas is. It's just going to be equal to the atmospheric pressure. We're doing everything in open atmosphere here, and that's going to be the pressure that's opposing the liquid on the outside. But that total pressure that we measure is going to be a sum of the pressure of the gas plus the pressure of any water vapor that's above the surface of the liquid. So this is something that we'll introduce in more detail in the next chapter, but whenever we have a liquid, there's going to be what's called a vapor pressure above it. So this is going to be that what happens whenever you have a liquid, some small portion of those liquid water molecules are going to escape the surface and exist in the gas phase. And so they create a small partial pressure of water vapor above the surface of the liquid. And the vapor pressure is temperature dependent. So depending on what temperature the experiment is being done at, and we'll talk more about this temperature dependence in the next chapter, you're going to have a different value for that water vapor pressure. Now, that number will typically be given to you, but you do have to account for it when you're doing problems like this, because we're going to use Dalton's law of partial pressure. We're going to use PV equals nRT typically, but we need just the pressure of the gas that's collected, which is oxygen in this case. And that pressure, though, above that surface is going to be the pressure of the oxygen, which is what we're interested in, plus the pressure of the water vapor. So we do have to account for both of those, as we'll see. So here's sort of a typical sample problem for this. So if we have acetylene, which is C2H2, a flammable gas that's used in torches sometimes, you can produce it by adding calcium carbide, CaC2, and just adding it to water. And then that's going to create a reaction that produces this as a gas. So if we do the reaction in that type of apparatus, we collect the acetylene gas over water at 23 degrees Celsius, where the total pressure is 738 torr, and the volume that we collect is 523 milliliters. If the vapor pressure of water is 21 torr at this temperature, how many grams of acetylene are produced? So there's going to be a few steps to doing this, but as we kind of already said, this involves Dalton's law, because we have to recognize that in an experiment like this, the total pressure of the gas that we collect, which is given here as 738 torr, but that's going to be a sum of the pressure of the gas we're collecting, which is C2H2 in this case, plus the water vapor pressure that we would have above the surface of the liquid. So this 738 torr is really the sum of those two things, which means if we want the partial pressure of C2H2, the product gas that we're collecting, we need to subtract from the total pressure minus the water vapor pressure. All right, so our total pressure is 738 torr. And then the water vapor pressure is 21 torr at this temperature. So that means the actual partial pressure of the product C2H2 is 717. So in problems like this, it's very common for students to forget to do this step. They don't remember why we even gave you the water vapor pressure, or they just focus directly on the total pressure and go straight from there into calculations. If you forget to do this, water vapor pressure is typically small compared to atmospheric pressure, but you'll get an answer then that's just a little bit off. So if you do a problem like this and your answer is a little bit off, a little bit bigger than it should be in particular, it probably means you forgot to do this step. So that's what we need, though. We need the pressure just of the gas that we're collecting. So we do that by difference. And then from there, we can use PV equals nRT to find the number of moles. So the number of moles of C2H2 is just going to be PV over RT, rearranging the ideal gas equation. So we need to do some conversions here, because pressure has to be in atmospheres. So the pressure in atmospheres is, we have 717 torr just for that gas that we're interested in. So we divide by 760 to get it into ATM. So 0.943 atmospheres of the gas. So we can use that as our first thing. The volume of the gas We don't have to change the volume, even though some of the pressure is water. Remember, both gases occupy the entire volume in a mixture. So the total volume will still be 523 milliliters, which has to be converted to liters for the ideal gas equation. So 0.523 is the volume given to us. Universal gas constant. And then the temperature is 23 degrees Celsius. So that has to be converted to Kelvin by adding 273. So that's going to be 296 in Kelvin. Okay. So this tells us that we have 0.0203 moles of C2H2. So that's kind of the typical thing you will do when you're starting one of these problems is you'll figure out the partial pressure of the gas you're collecting and then use PV equals nRT to find the number of moles. Now this one wants to know how many grams of that were produced, even though it's a gas, so mass is not the most useful unit. So we can just do the last step to find grams, which is to take the number of moles that we just found, 0.0203, and then multiply it by the molar mass. So the molar mass of that was given as 26.04 grams per mole. I think it was given. If not, it can be calculated. And that gives us to a mass of 0.529 grams. All right. I think that's the end of it, right? Oh, one more thing, sorry. So then the last question is, assuming we had 100% yield, how many grams of CaC2 were required to produce this? This is just a stoichiometry problem, so I don't really spend much time on it. But the mass of calcium carbide that would be required is, we figured out that there was 0.0203 moles of acetylene produced, and now it's just a stoichiometry problem. So we use mole ratios to figure out how many moles of calcium carbide that corresponds to. So they both have coefficients of 1, so it's just going to be a 1-to-1 mole ratio. So moles of C2H2 cancels out. That gives us how many moles of calcium carbide we need, which is the same number. And then its molar mass is 64.1. So 64.1 grams of CaC2 in 1 mole. So we did a lot of stoichiometry review today, just to remind you that it doesn't quite go away, unfortunately. And that tells us that we would need 1.30 grams of calcium carbide to produce that much acetylene. All right, so any questions on that? Go ahead. So a lot of these gas stoichiometry problems, you're going to use the ideal gas equation or Dalton's law or some combination of the two. But it's after you get the number of moles, it just becomes standard stoichiometry. Now, you guys are getting restless, but I'm not quite done yet. So hold your horses and get ready for the second bonus quiz. So I will exit out of the Teams thing here.